Hi everyone. In this video we're going to cover section 3.1, defining the derivative. The derivative is a huge important aspect of calculus and understanding all that we're learning here. The first new topic was limits, and now we take that one step further and we use limits to introduce this really crucial topic in calculus, and that's called the derivative. We'll talk about later on in the video what that is, but we first go back to secant and then what are called tangent lines. So a secant line is a line that intersects my curve at two different locations. So this picture should look familiar. And down here at the bottom, we've just got the slope of our secant line is f of x, that's a y value, minus f of a, that's another y value, over x minus a. Those are both of the x coordinates. And then in the picture on the right, we just kind of give a little bit of a different interpretation of the same concept. So I'm showing you the same thing, just two different interpretations. Instead of talking about two different points, A and X, we just kind of focus on the point A and then move some distance away. We add h units to it. So again, this is A and X, two different x coordinates. These are still two different x coordinates, but they're both defined in terms of the variable a, and then some distance away. And then we have f of a is the y coordinate, and f of a plus h is the other y coordinate. It's the y coordinate after I move some distance away from a. And then the slope of the secant line, just that formula is still a change in y over a change in x. But what's useful here is that the change in x, the denominator there, that's a plus h minus a, which is why there's just an h down there. So that kind of, the denominator gets a little bit easier to work with. Okay, so those are my secant lines. And where we start talking now about tangent lines is, what if I get a little bit closer and draw another secant line? Or what if I get closer still and draw another secant line that looks really messy? Well, tangent lines, what is the slope when I am at exactly that point A, right? So as I get smaller and smaller distances away from A, and I can do that the same thing on the other graph, and what helps here is as I get closer and closer to A, the distance away that I'm moving, it's shrinking. The value of h is getting smaller and smaller as I get closer and closer to A. And ultimately, when I'm at the point A there, all right, and when I'm at the point A there, h is so small it is basically 0. And then that is our slope of a tangent line. And the way that we write both of these, and this is why we talked about limits in chapter 2, the way that we write both of these is that the slope, and so I'm going to write m of the tangent line is equal to, we introduce limits, the limit as h approaches 0. The h gets really, really small, which moves me from the orange line to the red line to the blue line to ultimately the green line, the green tangent line. The other three are all secants. The limit as h approaches 0 of f of a plus h minus f of a over h. Okay, that's what that formula looks like for the right representation. And then on the left, the slope of my tangent line, this one is the limit as, now it's as x approaches a, because the x value is getting closer and closer to the a value, of f of x minus f of a divided by x minus a. Again, they're both similar. They accomplish the same task. They give me the slope of the tangent line, but they're just two different interpretations of this topic. Before we get to the next slide and stating the formal definition, I just want to do something I think it's kind of cool. We are looking at the graph of y equals the square root of x. And let's just talk about this point 0.5 right here, and there's a y coordinate. The square root of 0.5 looks like it's 0.6-ish, 0.6 something. Okay, that's not the point here. If I draw a tangent line on here, I'm ultimately going to erase it. Right? The tangent line, that's just an approximation of what the tangent line would be for this curve at that point. All right? But what we can do is we can zoom in. See what this looks like here. I can zoom in really, really close at that point And my curve, no matter how curvy it is, as I get closer and closer and zoom in further and further at that point, okay, what the graph looks like as I get closer and closer is a straight line, right? So I don't care how curvy of a curve you draw, if you zoom in on any single point, that curve looks like a straight line. And the term that we sometimes use is it appears to be locally linear right around this point. Oops, I didn't mean to do that. It appears to be locally linear right around that point. It really, really looks like a straight line. Okay, and that would be the slope. The slope of that straight line would be the slope of the tangent line at that point. Okay, so that's what we're finding as we move through the beginning of this section 3.1, and then as we go further into chapter 3. All right, now to start out this next slide, we have the formally stated definitions that I kind of already wrote down previously. If I have a function that's defined over an open interval containing a, then the tangent line at the point A is the line that passes through the point a comma of f of a, and it has this slope. It's that limit as x approaches a, f of x minus f of a over x minus a, provided that that limit exists. Or the other representation interpretation is the limit as h approaches 0, f of a plus h minus f of a over h. And we refer to these as 3.3 and 3.4. And as we go through some examples, I will use one or the other to answer the question. Okay, I'll give you examples using both, so you can kind of see how they work differently. Maybe you like one better than the other, but I'll use both in this video. Okay, so let's scroll down a bit and pull up my first example. All right, I want to find the equation of the tangent line to the graph of f of x equals x squared at x equals 3. And for this one, I am going to use the 3.3 formula, the top formula there, all right? So the way that this works, the way that we substitute in, I'm going to write the slope of my tangent line is equal to the limit as x approaches. Now, instead of writing the a, I'm going to write the point that we are talking about in this problem. X approaches 3. Okay, that's the first piece. And then it says f of x, my function, minus f of a, and again, instead of writing a, I'm going to replace that with 3, divided by x minus a, which is 3. So I've just replaced all the a's with 3's. All right, now the function is f of x equals x squared. I'm going to find f of 3 because I need to use that in my formula, in my slope formula. F of 3 squared is 9. All right, so let's go on to our next step of this problem. The slope of the tangent line is equal to the limit, and I'm going to write this every single time until I actually take the limit. F of x is x squared. I'm writing down the function, so that's this part. Minus f of 3 is 9. Oops, I lost part of my equal sign there from earlier. There we go. X squared minus 9 divided by x minus 3. So all I did was I substituted up in the numerator. All right, now in order to take this limit, I need to do some simplifying. All right, so to simplify, limit as x approaches 3, I can factor up in my numerator x plus 3 times x minus 3 divided by x minus 3. Hey, look at that. My x minus 3's cancel out. Now I can evaluate the limit. 3 plus 3 equals 6. So 6 is my slope. It's supposed to be underlining there. There we go. All right, that's pretty great. We found the slope at the point x equals 3, and that's the argument here. The exact slope at 3, even though that f of x equals x squared is a curvy line, the exact slope at the point 3, comma 9, the slope is 6. Now, we do have another step to this problem, so I'm going to scroll over a little bit because they want the equation of the line, the tangent line. So that's the slope, right? To get the equation of the tangent line, I'll write the word tangent there we go, the equation of the tangent line, we're going to use our point slope formula. Y minus y1 equals m times x minus x1, ultimately writing our equation in y equals mx plus b form. I can substitute into that point slope formula y minus, oh, and I didn't write this down. The point that I'm going to use, I'm sorry, I should have said this earlier. The point that I'm going to use is what we've already been kind of working with, is 3 comma 9, excuse me. This is the point that we were working with. X equals 3, the y coordinate that we got was 9, and then my m is 6. So plugging in y minus 9 equals 6 times x minus 3. I can simplify this by distributing 6x minus 18, add the 9 over, y equals 6x minus 9. Okay, so that is my tangent line. So if I were to plot the curve y equals x squared, and you can see this in OpenStax. I didn't take a screenshot of this, but if you go to OpenStax, you can kind of see a zoomed in image of this. Y equals x squared, y equals 6x minus 9. Those two graphs are going to just barely touch each other at the point 3 comma 9. All right, let's look at one more example using the 3.4 formula. Okay, so for the 3.4 formula, and the example that we're looking at here is the equation line. Find the equation of the tangent line to the graph. F of x, let me write this down, equals 1 over x at x equals 2. And while I'm doing this, why don't I just get the y coordinate? What is f of 2? Excuse me. That is 1/2. So we have the point 2 comma 1/2 on our curve. Okay, so the slope of the tangent line, and I'm using the 3.4 formula, is equal to the limit as h approaches 0. And you can look back at it in your notes if you want to. It's f of a plus h, so that's f of, 2 plus h minus f of 2 divided by h. Okay, so far so good. I'm just rewriting the formula, plugging in the a that we're given. The a is the number we're given. So let's now evaluate f of 2 plus h. So if I plug 2 plus h into my function, it looks like this. Well, let me rewrite the limit first. If I substitute 2 plus h into my function, it goes 1 over 2 plus h. Ooh, that looks a little ugly. That's okay. Minus 1 over 2, that's f of 2, divided by h. Oof. Fractions all over the place in this one. Our goal now is to simplify this complex fraction and ultimately take the limit. Now, I can't take the limit now because if I'm approaching 0, I can't put a 0 in the denominator. It's going to be undefined. So we've got to get this fraction to look a little bit cleaner before we can take the limit. And the way that we do that is we're going to multiply numerator and denominator by this guy, 2 times 2 plus h. I'm just putting these two denominators together with a multiplication sign between them. They're in parentheses, times 2 plus h. And what that does is it cancels out some things. Okay, so I'll show you what I mean. This is the limit. H is approaching 0. When I distribute this over here, the 2 plus h cancels out with the other 2 plus h. Okay, and leaves behind just a 2. When I distribute right here, the 2 cancels out that 2, and it leaves behind a minus parentheses 2 plus h. Then in the denominator, I have the h, I have the 2, I could have written that as 2h, and I have the 2 plus h. It still looks messy, but there's no more complex fraction here. There's just a single numerator and denominator. So technically it got a little bit cleaner. But we can do more. We can do better. Now, let's see. Let me go to change my writing utensil to white. There we go. This is equal to the limit as h approaches 0. I'm going to do this subtraction. 2 minus 2 in the numerator is 0. Oh, okay. And then a negative h in the numerator, all over 2h, so I am writing that differently, 2 plus h. So what can we do to simplify this? Well, I can cancel my h in the numerator with that h in the denominator. So this now becomes the limit. H goes to 0, -1 over 2 parentheses, 2 plus h. And finally, this one had a lot more work than the last one. I can take the limit because now if I substitute 0 in for my h, nothing bad happens. I don't get any negatives in the denominator. So finally, the slope of our tangent line is equal to -1 over 2 times 2 is 4. -1/4 is the slope at the point way up there, 2 comma 1/2. All right, so pause the video, go back and rewind if some of that didn't make sense. This one was way more complicated than the previous one. If the last one made sense, the only difference here is the algebra is harder. All right, if neither of these made sense, let me know. We can meet up and figure out what's going on here, okay? But again, the difference between the previous one and this one, just more algebra because we had a complex fraction. Let's do our last step here and get the equation of the line. So I've got y minus y1, mx minus x1. My y coordinate is 1/2. My slope is -1/4. X minus, I think it's 2, right? Yes, the x coordinate is 2. -1/4 x. Negative times negative is a plus. Quarter times 2 is 1/2. And then when you add that 1/2 over to the right-hand side, y equals -1/4 x plus 1, right? This -1/2 adds over to that positive 1/2, and you get 1. All right, so that was fairly involved, but that is the equation of the tangent line at the given point. All right, now moving on a little bit here. Actually, technically we're not moving on because we're using the same formula, but now you get to use the fancy new name. The derivative of a function at a point. F of x is our function defined in an open interval containing the point A. The derivative denoted, now let me zoom in on that a little bit. F, and do you see that little apostrophe there? There's a little apostrophe above the F, above and to the right a little bit. That is read, like when you read it out loud, F prime of A, okay? That is the notation that we use for the derivative of a function at a point. And all it is what we've been doing, okay? It's this limit as x approaches A, f of x minus f of A over x minus A. It's the slope of the secant line. So the derivative is a slope. The derivative of a function is a slope of a secant line. That's what it is. That's how we define it. We use the notation f prime of A, but it's the same thing that we found in the two examples on the previous slide. We're just adding in this notation. So we'll do then an example using this new notation. Let me scroll down a bit and pull my example up. Here we go. All right, and again, we're giving these 3.5 and 3.6 formulas. We're calling them 3.5 and 3.6. So just pay attention whether it says to use equation 3.5 or 3.6. Okay, now I have a different quadratic equation. F of x equals 3x squared minus 4x plus 1. And we're going to find f prime of 2 by using equation 3.5. So what does this look like? F prime of 2 is equal to the limit as x approaches 2 of f of x minus f of 2 over x minus 2. Again, I'm replacing all of the a's with the 2 that I'm given in this problem. So let me move this up a little bit higher. And then let's see. So what is f of x? My function is, oops, let me write my limit first. And you got to put that on every single step. And it's really annoying, and you might forget sometimes, and then I'll yell at you. Well, I'll yell at you virtually. But you should write the limit every time until you actually take the limit. All right. So f of x means I rewrite my function, 3x squared minus 4x plus 1. F of 2, all right, so what do I get when I evaluate 2 in the function? Well, let's see. F of 2 is equal to 3 times 2 squared minus 4 times 2 plus 1. 2 squared is 4, times 3 is 12, minus 8 is 4, plus 1 is 5. So my y coordinate would be 5. Okay, so 3x squared minus 4x plus 1 minus f of 2 is 5. So there's my f of x, there's my f of 2, over x minus 2. I need to take the limit. I can't yet because 2 minus 2 in the denominator, it won't work out. So let's simplify the numerator, and then I think we're going to have to factor again. Limit x approaches 2. What do I get up in the numerator? 3x squared minus 4x. 1 minus 5 is negative 4 over x minus 2. And then let's see if we can factor that. X minus 2 is in the denominator. Numerator is a trinomial. It's going to factor into two binomials. I need a 3x and an x. And the factors of 4, I think it's going to be 2 and 2. It could be 4 and 1, but here's where you use the denominator to help you out because that's a 2. That tells me that it's probably 2 and 2. Okay, and since it's x minus 2, this is probably x minus 2. And then that would make this one have to be 3x plus 2. But I'm still going to do the check, right? So when I do the check, 2 times x and negative 2 times 3x is negative 6x. Negative 6 add 2. Hey, that's the negative 4 that we had in the middle before. So that means my factoring is correct. Because it is correct, I can cancel the common factor. And then what's left, the limit as x approaches 2 of 3x plus 2, I can just evaluate that limit. 3 times 2 plus 2 is 8. And that is f prime of 2. The derivative at the point 2. Derivative, slope, use them interchangeably. Interchangeably? I think that's a word. It might not be, but it's okay. The derivative is the slope of the tangent line at the point. So 8 in this problem is a slope. So now we go back to the topic of position and velocity, and we already talked about average velocity. Well, what about instantaneous velocity, right? That is the slope at that exact moment in time. It is the rate of change at that exact moment in time. So if I use a position function, s of t, then the velocity function is the derivative, s prime of t. The derivative at that point, that would be the instantaneous rate of change. And so it's the limit as t approaches a of s of t minus s of a over t minus a. Actually, let me just correct something there. In the text, they don't use v of t. They use v of a at some point a, s prime of a. So I'm just switching those t's to a's. All right, but it is the same idea, the same concept. Okay, so we're going from average velocity. If I take the limit as that change gets small, then it becomes the instantaneous velocity. And we'll see in this example, our function s of t, pause the video if you want to read through the entire example, negative 16t squared plus 64. I want the instantaneous velocity 1 second after it has dropped. All right, so this is s prime of 1, s prime of 1, and that is the velocity at 1 second is the limit as t approaches 1 of s of t, I'll rewrite my function, minus s of 1 divided by t minus 1. So let's see what we get here. My s function, negative 16t squared plus 64 minus s of 1. So what is the position of this rock after 1 second? S of 1, negative 16 times 1 squared plus 64. 64 minus 16 is 54, 48. 64 minus 48 divided by t minus 1. All right, well, let's keep going here. Limit as t approaches 1 of negative 16 t squared, 64 minus 48. Let's see, what is that going to be? I think it's 16, 48, 58, 64. Yeah, 16. So that would be plus 16 divided by t minus 1. All right, we're getting somewhere. I see a common factor of 16, but I'm actually going to factor out a negative 16 because it'll help you to see what happens next. So I'm going to scroll up. The limit as t approaches 1 of negative 16 is my factor, parentheses, t squared minus 1. Okay, so I didn't say this. The negative, if I factor it out of the first term becomes positive, and if I factor it out of the second term becomes negative. Now my t squared minus 1 becomes, let's see, limit t approaches 1, negative 16, t plus 1, this is a difference of squares, t minus 1, t minus 1, oh good, cancel. That was what was messing things up all along. That's kind of the goal in all of these slope problems, is to find something to cancel out the denominator. Do some algebra, do some factoring, use a conjugate sometimes, and get that denominator to cancel out. Because now I can substitute my limit in, negative 16 times 1 plus 1, which usually is 2, is negative 32. All right, so what does that mean? Well, the ball is traveling. I think they give me the units in this one, negative 32, or no, it's a rock, feet per second. After 1 second of falling, it's traveling negative 32 feet per second. That's how fast it's falling. This last example I'm posting with the solution already done. I don't want to add a whole ton of runtime to this video because I know I'm already running a little bit long, but it's an application to economics really. And here we have a toy company, and they set the price of their product at P equals negative 0.01x plus $400 per gaming system. That's a formula that models the price of the product as a function of the number of systems sold. Okay, and then the cost function is given by 100x plus $10,000. That's the cost of manufacturing X systems. Then it says find the rate of change of the profit. And profit, I don't know if you knew this, but profit equals revenue minus cost. Again, I'm going through the overview quickly. You could read this, pause it, and read it if you want to understand it more fully. But it says find the rate of change of the profit when 10,000 games are produced. Rate of change, derivative, slope at a point. That's a big thing there. So when you see the words rate of change, that means derivative, that means slope, right? That means f of a plus h minus f of a over h, or f of x minus f of a over x minus a, and then the limit. All right, but what happens is when we go through the calculus of this problem, and they say, all right, here we're going to take revenue minus cost, here's our revenue, here's our profit function, and then the derivative at 10,000, here's all the work that's going on there. Okay, the purpose of this example is not for you to understand all of the economics. Okay, even the calculus I'm breezing through, but it's what we can use this for. All right, and that's the end of the problem. So after we get through all the calculus, we find that the rate of change is 100. What the heck does all that mean? And here's the big important part. Because the rate of change of the profit of producing 10,000 gaming systems is positive, and P of 10,000 is positive, greater than 0 means positive number, what that tells the company is increase production, right? Your profit is positive and it's increasing. So increase production and you will make more profit. So calculus has tons of applications to economics. It has tons of applications to lots and lots of fields outside of mathematics in terms of optimizing, helping to make educated decisions about what to do in certain scenarios. So that's just one quick example that I really breeze through because I just want to talk about this here at the bottom. If the rate of change is positive and we're making money, then hey, increase production and you're going to make more money. Cool. That's how calculus can help you to make informed decisions as a company. All right. That is the end of the video. If you have questions about these topics, the algebra has gotten a little bit more involved. If you're struggling, please reach out. Let me know. I want to help you. If you're struggling, if you're on top of all of this and perfectly okay, then pat yourself on the back. That's great because some of this can be pretty challenging. All right. Thank you very much for listening. I hope you have a wonderful day.